What we're going to do is we're going to minimize that error function now instead of our previous error function. How do we do that? Pretty straightforward. Same thing. We start with our e. All right. We're doing a minimization. We take the derivative with respect to the parameter d. That's the first one we're going to do. That generates this equation for us. We can use that to solve for d. And d is just this beautiful a x bar. X bar is the average of the x's plus b y bar. That's what these terms here are. Okay, so this now I've got an expression for d in terms of a and b. So I can substitute that back in, and I get this kind of ugly expression that we'll make beautiful in a minute. So I've now plugged these in, so there's no more d's in there. And look at that. That now looks very similar to the expression we had before, except now we've got this, these means subtracted. So if I stack up all my x's, x minus x bars here, and y's minus y bar there, and I'm actually going to call that matrix U, because I do, I can write this whole thing as UH transpose UH, where H now is this parameter AB. Remember, we got rid of D, we solved for D in terms of AB, and now we just have to solve for A and B. Okay, so now that we have an expression for E in terms of U, which are known from the x's and y's, and H, which is our parameter vector, in order to solve for H, what do? Same thing, we take the derivative of E with respect to H, repeat that equation, set that equal to 0, and that should start to look vaguely, annoyingly familiar, right? We have this matrix here, U transpose U, which is just made up of the x minus x bars stacked up, y minus y bars stacked up, transpose, whatever, times my parameter equals 0. Remember what equations equal 0 are? Those were homogeneous equations. Aha. All right, so the solution to U transpose H equals 0, well, the dumb solution is set H equal to 0. We said that wasn't going to work. Remember when we did the essential matrix and when we did calibration and all that stuff? We said, no, since we have everything okay up to a scale factor, what we're going to do is we're going to set the magnitude of H equal to 1. Now, in this particular case, we were going to do that eventually anyway, because remember A and B, which is what H is here, were the components of the unit direction of that line. So A and B have to be a unit vector, so we might as well just set the magnitude of H equal to 1. And so remember how you can solve that? You can do that whole SVD eigenvector thing again. So given U transpose U, you can find the eigenvector with the smallest eigenvalue, and that's your solution to, for H. I'm showing you this as a way of talking about that the right thing to do is perpendicularly squares. Here's how you do perpendicularly squares. And now the question that you really should be asking is, why is perpendicularly squares the right thing to do? Well, it's because we have in mind a particular model of noise. The model of noise we have, and we're going to refer to it as a generative model, because I have a model of how the noise is actually put within the system. Essentially, we have a particular model that we believe in. Computer vision, you have to have faith. The model that we believe is there's actually some real line underneath, and that each point has been perturbed off that line, here it's written as epsilon, by some Gaussian noise that has moved you off that line. And the probability of a Gaussian goes down by a function of what? X squared. So if you wanted to find the most likely solution, you would want to find the points that make the data that you're observing most likely. So those would be the ones where the sum of the square distances are the least, because, and just thinking about the Gaussian, won't go into too much detail, if you assume all those points were independently done, so the probability of getting all those points is just the product of those probabilities. The product of those probabilities is the product of all those Gaussians. Those Gaussians go e to the minus x squareds. When you multiply all those e to the minus x squareds, right, you just sum up all of those x squareds. And so whatever makes that sum of square difference the smallest, right, will be the highest probability. And so there's a whole bunch of assumptions going on underneath here in terms of the probability distributions and being independent and all that kind of stuff. But basically this idea of minimizing the perpendicular least squares comes from this idea that closer points are more likely, right? It's more likely a point will land closer to a line than further away from that line if the point actually came from the line. Got that? That's important to remember for our next lesson. All right, so that's written here in this equation. Basically, we're saying the point xy that we actually measure is just some real point on the line, uv, okay, that has been perturbed in the direction perpendicular to that line, AB, that's the line that we were solving for, and the perturbation has been some amount of noise that came from a Gaussian with zero mean and some standard deviation sigma, or variance sigma squared. So for the line fitting, or in this case model fitting generator, this is our underlying generative model, that it is a Gaussian perturbation. It turns out that that works fine when you actually have Gaussian noise. Turns out it doesn't work so great when you have some very, so we say, non-Gaussian noise, okay? So here in this picture, I've got a bunch of red points, and fitting the line through those points, okay, not very exciting. Actually, I probably should have had those points spread out. This is a problem when you steal some other people's slides, and you say, you know, I should have spread out those lines a little bit. But even with all of those points sitting right on the line, okay, I'm going to add one more point, all right, just one. And it's not going to be a nice point. It's going to be if it were a Gaussian point, it would be very hard to get far away. Let's suppose my points actually are made up of a bunch of points that are perturbed by the Gaussian off the line, plus evil Megan came in and sprinkled a few just nasty points. What would happen? Well, here's just one nasty point, bang. This one point out here makes this line the quote, best solution for all of those points. Now, many of you have seen this before for robust fitting. Bear with me. That point is one of our outliers. It doesn't come from the model that we have. And our model is actually made up of two parts. Our model is that there's a line and that there's a little bit of Gaussian noise added, that there's Gaussian noise added to the points off the line. This model is the evil Megan model, and we don't even know about that. But we would like to sort of be immune to the evil Megan model. So the question is, how can we do that? And you know, why is the evil Megan model so annoying to us? Well, the real problem is that squared error, right? So the bigger the error gets, you square its effect. That heavily penalizes outliers. So outliers can have much more of an effect on our model fitting than we really want them to have. So the question is how to deal with that. So one way of dealing with it that we're going to just talk about today, we're going to do it differently next time, is what are called robust estimators. And robust estimators say, instead of minimizing the sum of squares, okay, instead we're going to try to minimize some function rho. And rho is going to be a function of two things. R here is for the residual. It's the delta. It is how far off the point is from your model. So for fitting lines, it's how far away the point is from the line. So that's our error that we were using before, and before we were just squaring that. We're going to do some other function, and it's also going to have a scale parameter sigma, okay, or a robust measure parameter sigma. There are lots and lots and lots of robust estimators. We're not going to talk a lot about them. I'm just going to show you one example because it works very simply. So here's one. This is rho as a function of u. U is just going to be that residual, that error. And here's my sigma parameter. And the function that I'm going to minimize is just going to be u squared over sigma squared plus u squared. So let's think a little bit about how that function works, what it looks like. So this is just this function y equals x squared, okay? So for y equals x squared, you can see that it grows really quickly as x grows, and that was the problem that we were trying to fix. Let's think about what happens for small values of u versus large values of u, okay? So if we pick some sigma squared, when u is small compared to sigma, sigma squared plus u squared is about sigma squared. So that means the entire function is approximately u squared over sigma squared. So that just grows by u squared the way our original function did. And so it looks kind of parabolic to start with. But what happens when u becomes really large? Well, when u becomes really large, the robust estimator here becomes almost u squared over u squared, or 1. And that's what this value is here, out here. Okay, so the idea is as your error grows, it starts going up as a quadratic, just like our regular mean squared error, or just like our regular sum of squared errors. It goes up quadratically, but then it starts to level out, and that's what you're seeing here, is it comes up and it levels out. Now, where it levels out, that's a function of what the sigma is. Okay, so for a very small sigma, it levels out quickly. For large sigmas, it levels out much more slowly. So here's an example. Remember, we're going to, here's the same set of points. Aha! We have now foiled the evil Megan point, right? So we have this point here, and you'll notice that this line goes right through those other points. It's as if it ignored this point. Now, it didn't totally ignore the point. It gave it a constant weight, but it didn't matter whether that point was here or here or here or really far away, because once that residual got too big, it got a constant weight. Points that are nearby, they have the square error weight that we had before. So this is what it looks like when you get the scale just right. This is like Goldilocks picking the first bowl the first time. Never happens. Okay? At least not when I tell my kids, because then it would shorten the story and they wouldn't be asleep yet, so what good is that? If I set the scale too small, I get this weird line, right? Well, basically what's happened is every point is giving it a constant error, and it's just kind of going somewhere near all of the points. And also, if I set my scale too large, remember, if sigma squared is too big, then it's just like regular least squares. So I get the wrong solution again. So these robust estimators are powerful, but you do have to have an explicit, not only do you have to have an explicit choice of scale, it's pretty sensitive to your choice of scale. The method that we're going to talk about next time also has some scale parameters for the noise that we have to look at, but it's going to be much less sensitive to that. All right, we're going to stop here. We've taken a brief look at model fitting as really being a robust estimation problem. So for transforms, you want to estimate the transform, and you want to be able to do that robustly. And we use robust error functions to help. But what we're going to look at next time is a more algorithmic approach to doing this. Famous method, actually invented by a very good friend of mine. He's older than I am, so I'm not quite that old, that we'll talk about. And what's cool is it's a little bit more computer science oriented, and this is a computer science class, so that's great. And it's nice we can use a little bit of combinatoric analysis to show exactly how good it is. And the other thing is, it is used all the time. So you can say, well, Bobick finally is going to teach me something useful. Come back next time. All right, welcome back to Computer Vision. Last time we were talking about still estimating these transforms, and we're talking about how it was a model fitting problem. And one way of doing it robustly, because we'd have some bad matches, was to use these robust error functions. And I promised you, I always deliver on my promises, that the next time we would look at a more algorithmic approach, and sort of a more CS-oriented approach. So to remind you, our feature-based alignment algorithm is first extract some features, compute some putative matches, some possible ones based on the descriptors. And remember last time we looked at this ratio of the best match to the second best match, and we said, oh, you know, that's a good way of getting rid of some of our bad matches. And then the algorithm was supposed to do the following. It was supposed to loop until we were happy, hypothesizing a transform, and I'll say actually from some matches. And then we were going to verify the transform by looking for other matches that were consistent with the transform that we had solved for. And that's really fundamentally what we're going to do today, is talk about finding consistent matches. Some best matches are correct. That is, you pull out the best one, and it really is the right point. But some of them are not. The most important thing, though, back like we did in the Huff transform, the ones that are not are just sort of random. They're voting for Mickey Mouse, Santa Claus, Donald Duck. They're not all voting for some other particular wrong transformation. Not that there's anything wrong with Donald Duck, but he would make a poor governor. Although given some of the other governors, whatever. Anyway, so what we need to do is we want to find the right ones so that we can compute the pose, the transform, the fundamental matrix, whatever it is, the model. Okay, so this is the model that we want to compute. And today we're going to talk about this algorithm called random sample consensus, or RANSAC. So To talk about how this works, go back to our simplest example of fitting a line. So here we have some points, and if I were to ask you to